All right. Today we're going to talk about 14.6, triple integrals. And these are really just an extension of the double integrals that we've been doing. Just like when you did a single integral, when you first saw a single integral, let's say you were finding the area between two curves, okay, from, let's say, A to B. Okay, I'm going to relate it to something that I know we're familiar with. If we want this area, let's say this function here is f of x, y equals f of x, this one is g of x. Okay, you could do that with a single integral. And you take the top one, this y value minus this y value. Okay, so g of x minus f of x dA, or not dA, but dx. Okay, and your x goes from A to B. Okay, in last chapter, we saw that we could find the same, and this dx, that's the width right here, that tiny dx that you multiply by each of these heights. And when you add all those up, you get the area. Now, we saw in the last section that you could do this also with the double integral, where you're just adding up all the tiny dAs. Each tiny dA you add up throughout the entire region. Okay, and you have no integrand, or your integrand is just 1. You could think of it as a 1 times a dA. Okay, and that dA would be a dy dx. Okay, and y would go from the lower y, smaller y, to the bigger y. So from f of x to g of x. And then x would go from A to B. Okay, it's pretty easy to see that what happens after you evaluate the first one, that gives you the antiderivative dy is y, as y goes from f of x to g of x. So that's going to be, as you plug those in for y, g of x minus f of x. And this becomes your integrand. Okay, so this is going to be equal to A to B of g of x minus f of x times your dx. So right here, you can use a single integral to find area under a curve or area between two curves, or you could use a double integral. In the case of the double integral, you don't have an integrand, okay, or your integrand's just 1. After the first step, notice these are now identical, okay? So in the same way, we can find a triple integral. In a triple integral, we could use a triple integral to find volume, but we can also use a double integral to find volume. So think about some kind of a region here. Let's say on the x, so on the x-axis, you're going from A to B. On the y-axis, you're going from C to D. So your region in the xy plane is going to be this, okay? And let's say we're finding the volume in between two surfaces directly above here. Okay, so if we've got, so let's say we've got a surface up here. That surface might not be a plane, just some kind of a surface up here. And let's call that g of xy, because that's a z value. And then let's say you've got another surface. You could go all the way from z value of 0 all the way up to here, and you'd be finding the volume below that surface. But let's say we've got another surface somewhere around here. Okay, and let's say this surface is f of xy. Okay, and we want to find the volume in between these two surfaces. Okay, so kind of like a funny looking ice cube. Okay, so we can do that with a double integral, the double integral of the top surface minus the bottom surface, so g of xy minus f of xy over your entire region down here, so times your dA. Okay, and if we call that dA, actually let's call it a dx dy. We know that's our dA. So each one of these, think about it, each one of these tiny little dAs made up of a dx times a dy. Here's your dy, here's your dx. And you're finding, if you go up to this, that's going to give you a little section of this one, up to some little section of this one. We want to find the volume of each of these rectangular prisms. So each one of these is going to be a rectangular prism. And as they get infinitely small, we can think of their z values becoming fairly constant, okay? So the height of this thing is the g of xy minus the f of xy, and then you're multiplying by the area of the base, that dA down there, okay? So your x is going to go from A to B, and your y is going to go from C to D. In this case, it works out nicely. Your region that you're integrating over is a rectangle, so these are all constants. That's not always going to be the case. Okay? But just like this, we could use to find area, and we could use a double integral to find area. We could also use a triple integral to find volume. This thing right here is it gives us a volume, but we could also use a triple integral and just add up all of the tiny dv's. Each one of these, if you think about each one of these as some kind of a tiny little volume made up of that's a dv, which is equal to a dx, dy, dz. Doesn't matter which order you write those in. Length times width times height gives you a tiny dv. So we're adding up all of these dv's to get a volume. Okay, so in this case, it looks like it's easiest to do the dz first, and then the dx dy. Z is going from this surface, this z value, to this c value. So you've got a f of xy up to a g of xy. Okay, and then after you do that first, the dz, now you're going to, the dx, oh, sorry, that's a dx dy. Now you do the dx dy. And that region is going to be the region that you've projected onto the xy plane. If you've already taken care of the z's, now you're projecting onto the xy plane, and that's this region down here. Okay, so your x goes from A to B, and your y goes from C to D. Okay, and you could do this in different orders also. This one doesn't really lend itself to doing, let's say, the y's first, from going this left to right. So this side over here of your region over to this side over here. If you did the y's first, you'd now have to project this thing onto the xz plane. So you'd project it over here onto the xz plane, and this thing looks like these could be a problem, okay? Because since this goes up and down, you might not be going from the same y to this on the right to the same y on the left, that the same function as you would be for most of the region, okay? So let's look at an example. Let's look at kind of the most simple example to find volume. Let's say we've got x plus y plus z equal to 1. Okay, and we know what this region looks like. X, y, z. We hit 1 on all three, and we're going to find the volume in the first octant bounded by the coordinate planes and this surface right here. And this surface would be z equals, it's your function of x and y, equals 1 minus x minus y. Okay, so if we calculate this volume, we could do it with a double integral, or we could do it with a triple integral. Let's do a triple integral. We're going to add up the dv's, and that dv, we'll do the z's first. dz, let's do dy dx. So z goes from down here, from the bottom, the smallest z value, which is 0, up to the top. And on the entire region, the biggest z is going to be on this surface, so 1 minus x minus y. Okay, and then we can do the y's next. And when we do the y's next, I always like to redraw this. Since we've done the z's, I'm going to draw what this projection is onto the xy plane. Okay, on the xy plane, we're going from, now we'll do the y's next. We know that this hits 1, positive 1 on both the xy planes. And then this is going to be y equals 1 minus x. So the y goes from 0 to 1 minus x, and the x goes from 0 to 1. Okay, that's going to give you volume. Now, another way you could have done this with a double integral of your function, which was 1 minus x minus y, dy dx, 0 to 1 minus x, and 0 to 1. Okay, these give you the same thing. And you can see after you do this first one, after you evaluate with respect to z, this thing turns into your integrand, and you end up with the same thing. Now, I want to talk about one more thing. We could change this order, dz, dy, dx, to 6 different ways. So some of the problems, they're going to have you do changing the order of integration, and you can see that you should always get the same answer if you did it correctly. Okay, there are 6 different ways. We could do dz dy dx, we could do dz dx dy, we could do dy dz dx, we could do dy dx dz, we could do dx dy dz, and dx dz dy. Okay, let's do the y's first, just for fun. Let's say we do dy dz dx. Okay, so this same region. So we're going to go, y goes from, and now you're going to travel parallel to the y-axis. So you have the smallest y for this region is back here, the left side of this thing, where the y value is 0. And the right side is going to be, each one of these is going to go this way until it hits this surface. And this surface, if you solve this thing for y, you'll get 1 minus x minus z. Okay. Now, once you've done the y's, now you're going to project this entire thing onto the xz plane. And on the xz plane, conveniently, your x hits at 1, your z hits at 1. Okay, so this is going to be z equals 1 minus x. So if we do the z's next, now your z goes from 0 to 1 minus x, and x goes from 0 to 1. Okay? I'm not going to do all of them, all 6, but you get the idea, hopefully. Okay. Now I'm going to look at example 2 from our book, which is changing the order of integration. Okay. Now number 2 from your textbook looks like this. Okay, you've got this solid right here, which is kind of convenient that this thing is a rectangular prism. It lends itself to doing the z's first. Okay, you don't have to do the z's first. And I'm going to show you doing the z's first, and then maybe doing the x's first. Okay, so this original question is just this. Okay, from this, you should be able to draw this thing, draw this solid. Okay, so let's just write this down and think through how we do that. Okay, your z goes from 1 to 3. And then your x and your y both go, your y goes from x to rad pi over 2, and x goes from 0 to rad pi over 2. Okay, so let's write that down. This is example 3 on page 1016. Okay, so we've got the integral from 0 to rad pi over 2, and then the integral from x to rad pi over 2, and then the integral from 1 to 3 of sine of y squared dz dy dx. Now what I want you to notice here, we're not finding volume, okay? We have an integrand. So what are we actually finding here? Well, what we're finding, let me make sure we have that right. What we're finding is each of these dv's, that's a dv, gets multiplied by some value. Okay, so just like when we integrate, you've got a value of a function, and that value gets multiplied by each of your differentials, and you add those up. So this could be something like, maybe this is your function for a mass density. Maybe this is grams per centimeters cubed. Maybe that's a volume density. Okay, and if that's a volume density and you're multiplying by a dv, and that dv is going to be in something like centimeters cubed. And as you can see, each of these that you multiply by this, the centimeters cubes cancel, and you're just adding up a bunch of masses in grams. Okay, it could be a charge density. Okay, it really could be almost anything that you're taking and you're multiplying by your dv's, and then you're adding them up. Okay, so let's think how we would draw this through this. Z goes from 1 to 3. Y goes from y equals x to y equals rad 2. I'm going to draw this in the xy plane first. In the xy plane, y goes from y equals x to y equals rad pi over 2. Okay, so this right here is rad pi over 2. And since this is the line y equals x, we know that this point here is going to be rad pi over 2, comma rad pi over 2. Okay, we're integrating over this region here. Now your x goes, well, we know the x goes from 0 to rad pi over 2. So that gives us this region. Call that R. Now the z goes from 1 to 3. So if we draw this, x, y, and z. So this is going to be y equals x. And we'll draw y equals rad pi over 2. So let's say we've got here rad pi over 2. And we're going to draw parallel to the x-axis as we go out here because our y value is constant. Okay, and now we're going to draw, say, 1, 2, 3. And at 3, we draw this same exact shape. And you've got your cylinder. Okay, so this right here is y equals x. In fact, this entire side is y equals x. That's a plane. Okay, this right here is the plane y equals rad pi over 2. So it's a little bit tricky to see this. These both look slanted, but this one is actually straight. It's parallel to the xz plane. This one is not. And this up here is z equals 3. And we want to go from z equals 1 to z equals 3. So we actually want to go, okay, maybe I'll dot that one so you can see that's in the back. And maybe we don't want to draw this in here. So we can see that we're only going from this down here to this here. Okay, so our z value goes from z equals 1, which is a constant, to z equals 3, which is why we get this here. And then when you project that down to the xy plane, you can see it's a little easier to see it here. Okay, now your y goes from y equals x up to y equals rad pi over 2, and then x goes, and you add those up as x goes from 0 to rad pi over 2. Okay, and you could evaluate that. I just want to work on the setup right now. But let's try to do this, and I'm going to switch the order of integration to, let's do sine of y squared. We'll do the let's do the dy first. dy, dz, dx. Okay, so now if I'm doing the y first, I want to go in the y direction from this side to this side. Remember, if you're going the y direction, you're going to go parallel to the y-axis. So like this point would match up to this point over here. This point would match up to this point. This point would match up to this point, and so on. You're going from this surface to this surface. And that's y equals x to y equals rad pi over 2. Okay, now here's where it gets tricky. Now, how do we do the dz dx? Well, now we've got to project this thing onto the xz plane. Okay, so let's look at what that looks like. On the xz plane, if we were to project this thing, and you've got to be able to visualize this, if this thing projects over here onto this plane, that would project over here. You would end up on this plane, okay, with a rectangle. So projecting this entire thing onto this, it's easier to draw here. Your x is going to go from 0 to 1, 0 to this point, right? This point right here, which is, we know up here, that's rad pi over 2. So x goes from here to rad pi over 2, and then our z goes from 1 to 3. So this is now our region for the dz dx. Okay, and since this is a rectangle, these are both constants and these are both constants. We could switch the order of these fairly easily, just making sure we switch these also, but they're going to be the same values. Okay, so now z would go from 1 to 3, and your x would go from 0 to rad pi over 2. Okay, I think that's good for now. One more thing I want to talk about is how you decide if you're going to do the y's first, the x's first, or the z's first. I'm going to show you a couple of pictures. Our book doesn't really describe them as type 1, type 2, type 3 regions, and I'm kind of glad they don't. I don't care what you call them, but the concept is actually pretty good. If you look at something like this, these two solids, if you're going to do a triple integral over these two solids, it's pretty clear, and hopefully I would like, it'd be good for you to be able to see that it would make the most sense to do the z's first. So when you do your integral in the order of integration, it makes sense to do the z's first because of the way that this is set up. If you do this z down at the bottom, which is this thing, u1 of xy, up to this z, u2 of xy, okay, those are going to be your limits of integration. Now, when you want to do the x and the y, you will project this thing down to the xy plane, and now this is your region. So at this point, you're either going to, this one, you're probably going to do the y's next, and then the x's, okay? That would make the most sense. This one down here, you're going to do the z's first, and we call it type 1 if you do the z's first. Okay, it's still type 1 if you swap these two, the y and the x. But don't worry about calling it type 1. I just want you to recognize here, you do the z's first. Okay, now when you do this one, if you think about this region here on the xy plane, it probably makes more sense to do the x's next, because you go from the smaller x to the bigger x, smaller x to the biggest x, bigger x, and you do that as y goes from this value to this value. Okay, now the other two types would be something like this, and usually it's fairly obvious which one you're going to do first. If you've got something like this, think about trying to do the z's first. You do the under part of this like muffler type of shape up to the top. It's going to be kind of a pain in the neck, and then project that down to the xy plane. It looks like it'd be easiest to do this direction first, from this surface back here up to this surface. So this right here, which is u1 of yz, that's your x value, to this x. So it makes sense to do the dx first, okay? In this one, it looks like it makes sense to do the y first, because this surface right here is a function of y, and this surface right here is a function of y. Or a function, I'm sorry, this is y as a function of x and z, and this y is a function of x and z. Okay, so you'd go from u1 of xz to u2 of xz, and you'd do the y's first. Okay, so that's represented down here. I think we can see it down here. Okay, so this is called a type 2. This is called the type 3. Don't worry about the types. I just want you to be able to see what makes sense to do first when you get a problem and they don't tell you which way you want to integrate first. There's one in our book that I think was interesting. If you look on page 1017, okay, let's look. So for example 4, and this one from the book is really interesting because it's kind of tricky and kind of hurts your head to think about which one you would want to do first. Okay, now think about this. It might be tempting to do the x's first, where x goes from this plane, x equals 1 minus y squared. Notice that's a plane, this plane back here. It's a plane, and it's a little tricky because that's not parallel to the yz plane. Okay, it's slanted. Notice this is x equals 1 minus y. So you've got a slanted plane here. If you go from there to this plane is x equals 3 minus y. Again, not parallel to the yz plane. If you do that one first, think about what happens. Then if you project this thing onto the xz plane, it's kind of messy, okay? Because this part would project down to, let's see, it would project to here, right? Okay, so then when you have to do the y's, focus that a little better. When you do the y's, now your y goes from this back end here where y is 0. Well, for part of it, you go y equals 0 to this plane right here, which is going to be y equals 3 minus x. But for the bulk of it over here, you're going from y equals 0 to this surface, which is going to be solve this thing for y equals 1 minus x. And then back here, this part back here, where your x goes from 0 to 1, well, now you're going from this plane, y equals, that would be rad 1 minus z, would be the back end, up to, as you move in the direction of the y-axis, this thing right here, which would be y equals 1 minus x, okay? So for this one, it really makes the most sense to do the z's first. And you can see that because when you do the z's first, your z for this entire region goes from z equals 0 up to this surface right here, which is going to be z equals 1 minus y squared. And when you project that down to the xy plane, well, now you've got this thing right here. And projecting that down to the xy plane, again, I will always draw this in the xy plane. Okay, you've got this thing. So I'm going to graph x equals 1 minus y and x equals 3 minus y. So x equals 1 minus y. Actually, it's y equals 1 minus x to y equals, if I solve these for y equals 3 minus x. So we'll start at 1, 3. We've got slopes of -1. And this is going to go to here. Okay, so that's going to be our region right there to set up the integral for the x's and the y's. So let's set it up. Triple integral, and let's just say we're doing a volume, so just a dz, dy, dx. Okay, so the z goes from 0 up to the top of the surface, which is 1 minus y squared. And the y is going to go from here to here, which is that's y equals 1 minus x, and this is y equals 3 minus x. And then the x is going to go, as you do those, you do all of those, as x goes from 0 to 1. Okay, so that by far is going to be the easiest to do if you do the z's first. Okay, and then the y's second. If you think about doing the x's second, you'd have to go from this x to this x for this section here, and then for here you'd have to go from this x to this x, and then here you'd have to go this x to this x. It's not that it's not possible, it's just sometimes way more difficult for certain orders of integration. All right, thank you all for watching. Just work through the problems on the assignment sheet, and we'll take any questions tomorrow.